Day 53, Honors Physics, Rotational and Translational Equilibrium, problem number 37, torque. The central object here is this boom, this crane, this part right here. And we're going to leave it at an angle. This is one of those where we can't lay it flat too easily. So this crane structure I have simplified as a free body force diagram over here. This is the crane at a 60-degree angle with the base of the crane where it's attached to the platform. I have a cable, T1, that's at 45 degrees with the horizontal this way. But if you look at the geometry of the problem, this angle right here, all the way between the horizontal and the crane, must be 60 degrees because it's alternate interior with this angle down here. So if that's a total of 60 degrees up there, that small angle, the actual angle of the cable with the crane, is 15 degrees. Right there must be 15 degrees. That's how I get the 15 up here in the diagram. That's the important number, the 15 there. The crane itself, the boom, is 60 tons, and it's a uniform crane, so that's in a dead center, 40 feet from each end. This is 40 feet here. I couldn't fit the feet in there. 40 feet from point A to there, and 40 feet from there to the end of the crane, 80 feet total. The crane weighs 60 tons. That's a force, that's a weight, so you can leave this in tons. So the answers will come out in tons. As noted in the notes, the attachment of a boom or an angled lever like this boom, attached to a platform or a wall, will have two components to the supporting or holding force. There'll be one force, but components. They'll have an Fy component and Fx component. So always draw these two components. We're going to be looking for those two components, plus we'll do a little bit of extra work here. But at the attachment point, you'll always have those two components. Here the platform is holding this up, and it's pushing in, keeping the boom from sliding backwards. So those are the directions of the two forces supporting the boom, the two components. So point A is my reference point for torque calculation. So here is my example of that, or my calculation of that. Clockwise torque equals counterclockwise torque with reference to point A. So at point A, the 60-ton force is trying to make the whole thing rotate clockwise. So that's my clockwise producing torque force, 60 newtons times the distance from point A, which is 40 feet, leave it in feet, times the sine of 30. That's the angle right there. That angle is 30 because, once again, looking at the crane, we have 60 degrees over here. If I drop a line straight down, say like from the dead center of the crane straight down here, and look at this triangle, that triangle right there, okay, that must be a 30, 60, 90 triangle. So the little angle I have from the center is 30 degrees, the complement of 60. That's how I got the 30 from the geometry. That's an important number because I have to use sine of 30, not sine of 90, because that force is at an angle with respect to the lever, the boom, of 30 degrees. And then the counterclockwise producing torque is this force right here. It's going to try to make the whole thing rotate this way. It's at a weird angle there, but that'll factor in when you use sine of 15. It's that force, T1, times its distance from point A, 80 feet, times the sine of 15 degrees, the angle it makes with the boom, not with the horizontal, not 45 degrees. So that'll give you T1. T1 will be some number that's known. Now, T1 will have components. That's the next part of the problem, way over here on the left. So you're going to come over here and find the components of T1. Now T1 is at a 45-degree angle with the horizontal, not with respect to the beam. So now we're looking at the regular Cartesian coordinate angles, not the angle with the boom. It's at a 45-degree angle with the horizontal, 45-degree angle with the vertical, and we know that T1, this is T1 here, the hypotenuse, so to speak, I can figure out the two legs. The shortcut would be just to take T1, that's already known, and divide by square root of 2, because it's a 45, 45, 90-degree triangle relationship. So I will know T1x and T1x and T1y, which would be a little bit less than T sub 1, but they'll be equal to each other. Now, looking back at the boom itself, okay? I'm not going to draw the components on the diagram right now. You could draw another diagram if you want, but bottom line is there'll only be two horizontal forces. Fx is pushing to the right, and the only other force to balance that is the x component of T1. So Fx, over here, Fx has to equal T1x, which I now know from over here. All right? So T1, going back up to the very top up here, T1x will have that component that we just figured out, which will be equal to Fx. So those are the only two forces. They have to balance translational equilibrium. So once I know T1x, I know Fx. That's part of what we're looking for here. It's just saying to find the components. And then up and down, T1 has that also component, the y component pulling down. It'll be pulling down a little bit. It'll be pulling down from this point, pulling down. I have that right here. And the 60 tons is down. And the only upward force is Fy. So Fy, up, vertically, is equal to the sum of the two downward forces to get the translational equilibrium. That has to equal the sum of the 60 plus the y component of T1, which is also down, which will add to the 60. So it's going to be like 70 or 80 or 90 tons, somewhere in there, depending on what T1y is. So Fy, up, equals the sum of the two down forces to get your translational equilibrium. If you wanted to find F itself, the overall force at the deck, where the boom attaches to the deck, it's F squared equals Fx squared plus F sub y squared, the two components, Pythagorize it, you can get the force F. They didn't ask you for that, but it did ask you for the tension. We got that earlier. That was the first thing we figured out. So that's a pretty involved problem. Good luck with that.